Okay, so where were we? So we're talking about the free particle quantum system, and it's okay. So what do we do? So this is pretty much the free particle, and everything I'm doing now is I'm just doing in one spatial dimension. All the things I'm talking about at this point really don't depend on what number of spatial dimensions you're in. So I might as well stick to one spatial dimension. And so then what you want to do, what happens is what you've got is that your Hilbert space is our c-valued functions on R. So this is your state space. And the only operators we really know about so far are the momentum operator, which is the thing you get from taking the action of translation on functions and the infinitesimal action of translations. Think of that as a Lie algebra representation, and you get the self-adjoint operator you get is P, which is minus I H bar d dq, where Q is the position. Okay, and then the only other operator that really appears is the Hamiltonian, which for a free particle is P squared over 2m. So if you like, 1 over 2m minus H bar squared Q squared. So this is the basic setup so far. Okay, and then the eigenfunctions of P, the kind of one-dimensional irreducible representations of translations are the eigenfunctions of P. These are just these things. What they're e to the I are e to the I beta small p over h bar q, which has eigenvalue small p, and that small and this will have the interpretation, a physical interpretation, as the momentum of the particle. Okay, so now we've got probably now and these things also are also eigenfunctions of the energy with eigenvalue p squared over 2m, which is just the kinetic energy. Okay, so now so the problem, the main problem we're running into is that these are not normalizable. In other words, the integral of e to the I p over h bar q squared q is infinite. So you can't take these have kind of an infinite norm in any kind of standard norm you want to put on functions. Okay, so that's the problem. So now what do we do about this? Well, the first thing to realize is that I haven't actually, I haven't actually told you which functions. So let's go back and talk about a couple different ways of dealing with this, of choosing our sets of our space of functions that we're going to actually use to really say exactly what we mean by the state space, and see if we can, what we have to do to start dealing with this problem. Okay, so there's one approach to this. So which function? Well, there's one approach. So one is that what physicists would say what you're doing is put this in a box. So put this system in a box, size L, and this is going to allow you to make things to make your the eigenfunctions of translation normalizable. And so what you're going to do is so you basically impose a periodicity condition that, so if you can think of it as just looking at periodic functions or just looking at functions on an interval 1 to L. And then what you find is that the eigenfunctions of P are e to the, what is it, e to the, how did I do this? E to the I2 pi over L n, and then that's over 2 pi n. Now where does the h bar go? E to the I n cubed. I guess this so P is then going to be 2 pi h bar, yeah, n h bar n q. I think this is right. Okay, and this is so this is going to have the eigenvalues are then going to be okay, and then the idea is that the eigenvalues take values, so n is z, so the eigenvalues take r, z are, these are normalizable. Well, the eigenvalues take discrete values, and the eigenvalues you can actually make them finite if you these are discrete, and one thing you can do is if you insist, if you take absolute value of n less than some big n, then you get a finite h is finite dimensional. Okay. So one thing that you can do that would totally solve all of your analytic problems is to work put things in a box of size L, and then you've got your momenta now instead of being discrete. Instead of being a continuous objects, take on these discrete values, and then as L goes to infinity, they become the spacing goes to 0. And then if you really want to completely get rid of all problems of analysis, then you just you also put some kind of cutoff. You only look at these for up to some finite value of n. This in some sense is kind of an ultraviolet cutoff. Means you only consider momenta up to up to this value in big N. Then this is finite dimensional. Then there's no analytic problems. There's no question of which functions to look at. It's basically all your state space is all linear combinations of these guys. Okay, and then but then you have to take, and then your problem is take how to take L goes to infinity and n goes to infinity. So you change your problem as to some specific problem of you have well-defined calculations, but you've got two limits you have to take and have to see what happens then. Okay, so that's this is one way of dealing with it. The second way is to take okay, so to take H to be, I'll call L2 of R. So it's all functions whose whose norm squared is finite. So restrict your attention to functions whose norm squared is finite or squared, that are square integral. And then, anyway, then this becomes an interesting and complicated question and analysis. I mean, the nice thing is that you've gotten rid of this problem. You get rid of this problem of taking limits, and maybe the way to say the nice thing that happens. Well, there are a couple nice things that happen. So advantages. Well, this space, if you go through the effort to kind of properly define this thing, of exactly what you mean by this, and get your theory of integration straight and your definition straight, then what you're going to find is that basically the dual, so H is isomorphic there's an obvious notion of dual, and this space and its dual space are isomorphic. And this was a nice property also working in finite dimensions. The point is that you if you're in finite dimensions, you also had you had this nice Hermitian inner product on here. The Hermitian inner product gave you an isomorphism between this and its dual, and you can and so all sorts of things then work out very nicely. Well, this also preserves this. So the fact that the standard inner product, Hermitian inner product of complex functions, gives you an isomorphism with a dual, and this is something that's called the precise statement of this is something called the Rhys representation lemma. So Rhys representation. I don't know if a theorem or a lemma or whatever, depending on how you do this. And this really says that you can go back and forth between a function and think about a linear functional on functions by taking the integral of minus infinity to infinity of f integrated against some other function. So a function always gives you a functional on functions this way, and the Rhys representation theorem says that this actually gives you a nice identification of nice isomorphism between these guys, and that things are going to behave very much like they did in finite dimensions and finite dimensional linear algebra. That you can go back and forth. You can use the inner product to go back and forth between this space and its dual. Okay, and so things work out much the way they did in linear algebra. Okay, that's one advantage. And then I guess I want to say that the other advantage, there's a second advantage of this, which is that if you take the Fourier transform preserves this. The Fourier transform of something that's L2 is L2, and not only does the Fourier transform takes you from L2 to L2, preserving the inner product. So the Fourier transform is a nice unitary isomorphism between this and itself. So those are the two big advantages. And then you have something. You also had something similar here, that you had the notion if you went from a function to its Fourier series, that was also a nice isomorphism between a finite dimensional space H thought of in terms of functions of Q, and the same finite dimensional space H thought of as in terms of the Fourier coefficients.
Is the first method somehow related to the Galerkin method?
Wait, sorry, I couldn't hear you.
Am I muted?
No. You did just say it was a little bit too fuzzy.
Is the first method somehow related or similar to the Galerkin method?
I'm sorry. I can hear you, but can you speak a little bit more slowly and clearly?
Oh, okay. So is the first method somehow similar or related to the Galerkin method?
To the which method?
Galerkin.
What, I don't understand that word. Which word?
I mean something in the PDE.
A Galerkin?
Galerkin. No, wait, sorry. What was the word? That
Galerkin.
Galerkin method?
Oh.
No. I'm not. Anyway, what was the Yeah, it's a good. Yeah. Actually,
Yeah. That's what that's how it happened. So.
I'm sorry. Yeah. I just couldn't hear. I didn't know what you that second word you're asking about. But this first method, I mean, this is very kind of naive. This is all just Fourier theory of Fourier series. It's very naive, and all of the all of the. The problem is that this could be very different. This is where all the trouble is going to come. Okay, this is here we're using a much more there's a more we're using much more sophisticated analysis in the definition of your integral and of what you mean by L2 and exactly what kind of linear functionals you talk about, and so we're using some more high-powered analysis here. And then you have to also be careful about how you define the Fourier transform in order for it to take L2 to L2. But if you do some hard work and analysis, then you get these nice two advantages. You get this isomorphism and the Fourier transform working nicely. Okay. Does that help? There. Okay. Anyway. Okay. Yeah, I don't know. I mean, this is really very, very naive. This is really just all this. This is just the theory of Fourier series, and it's true. You can anyways. Yes, I'm not saying anything very interesting mathematically here. Okay, let me go on then. The okay, but the problems. Okay, so now what I'm going to do, actually, so as I go on in this class, I think you should, sometimes I'm going to be trying to avoid talking about whatever the analytic problems might be going on. And I'm also, and as I do that, you can often assume that I've done one of these two things. You should assume when I'm talking about the state space, either I've put it, this is actually a cutoff state space where everything's working nicely, or I'm working with the L2 space and I'm doing something which doesn't hit the problems I'm going to talk about. Okay. So, but now the next question is, how do you really? Let me explain what the problems are, and how you actually legitimately deal with them. And so the problems. Okay. Problems. And this is, yeah, so this is the problems with two. Okay. So often I think, people who are writing a physics textbook are kind of assuming that they're dealing with something that, if you tried to make it precise, you would work with two, trying to do this L2 of R business. But it does have problems. One is that if you take the momentum P psi element of L2 of R does not imply that P psi element of L2 of R. Okay, and same with the Hamiltonian. So your problem is that you've got this nice, you set up this nice theory where this is your state space. But the one operator that you're interested in often will take things that are in the state space to things that are outside the state space. It's easy to come up with examples of functions that are in L2, but if you take their derivative, it's no longer in L2. Okay. So that's the one problem, and then the eigenfunctions. Functions of P are not in L2. So these are our problems. Okay, so the way to deal with this, so distributions are kind of mathematical language allows you to deal with this, and you kind of do this in two steps. The first thing you do, so two steps. First step is you get rid of you get rid of this problem by choosing a class of functions that's well behaved. Not only are they square integrable, but their derivatives are integrable, and they exist and are integrable, and so you define a space. I'll call it S of R. These are often called Schwartz functions, or they're often called test functions. That are which are kind of the definition technically is to say that these are functions that exist. The function and all of its derivatives exist, and the function and all of its derivatives all fall off faster than any polynomial. So you can integrate the function and all of its derivatives, and if you start hitting this with this operator and taking more derivatives, you're not going to leave that space. Okay, and also if you take the Fourier transform, you're not going to leave the space. And also, if you multiply this by powers of q, you're also not going to leave the space. So we would with good properties. So I won't write those out again. Properties. Okay. And yeah. So this you should think of as kind of very special, really nicely well-behaved functions. They and all their derivatives fall off very nicely. Every good property you would want a function to have, these guys have. And maybe a good example to keep in mind are polynomials times Gaussians. So a Gaussian is something that falls off exponentially as you go off to plus or minus infinity. It's like a bell curve, and if you multiply any of these by any kind of polynomial, you're still going to have this nice exponential fall off everywhere. And if you take the Fourier transform of these guys, you'll get another one of them. You'll stay within this class. If you take derivatives or if you take derivatives, you'll get another one of these. If you multiply by some powers of q, you'll get another one of these. So this is kind of a subclass of these test functions, which has all the right properties and which is also closed under the operations you care about. And often when you work with test functions, you often just think about these guys. Okay, but now the problem with this. Okay, so the problem with this is when we do this, we've lost the nice property of L2 that the dual of L2 is L2. So the problem is that the dual now actually what happens is that the dual in any sense, the problem is that the dual in some sense is much bigger. If you try to, with infinite dimensional spaces, if you try to make them smaller and smaller and more constrained, you get more and more possible linear functionals on them. And so here, but let's call the dual that's prime of R. Or this is supposed to be something like a prime here means dual, and you have to be careful about it. You have to be careful with exactly what you mean. You know, when is a you're kind of asking for linear functionals on an infinite dimensional space. So you have to put some kind of condition that you want, kind of some kind of continuity condition on, you know, on you want this linear map. These linear maps have some kind of continuity property, and so you have to you have to be a little bit careful about doing that. But if you do that, you can do this. And these things are often called tempered distributions. And I'll just call them distributions. Okay, I'll just call them distributions. Okay, and now okay, and then basically what you do is you use the transpose to move to get to take operators on S or to operators on it as prime of R. Okay, and so this is this transpose. I think I wrote this down last time. It's basically that if you and it's just this basic kind of fact about linear operators, that if you have a linear operator on the space, then you can get a linear operator on the dual space by kind of tautologically, by taking it acts on the linear operator by giving you the linear operator that says first to calculate the linear operator on a vector, first apply the operator to the vector, and then take the linear operator. So it's just the kind of coordinate independent analog. It's exactly the story about what's the transpose operator mean in finite dimensions, and just kind of in this context. And so then what happens when you do this is that you get the fact that these guys have every property that you want, that they behave very, very nicely. These guys behave very nicely on all the operators that you're interested in. Well, then so will these guys. Okay, and so you get nice so these behave well under action of P and of the Fourier transform, and even better, then you actually have, since then you also have that not only is the space of distributions preserved by acting on distributions by P, but it actually has the eigenfunctions of P are actually in the space. So the eigenfunctions of P are in. That's right. So this has these really nice properties. But let me and I'll start working. I'll work out some examples in a minute, and then maybe. Okay, yeah. So. Okay. So the picture we have is that we've got test functions, and these guys are in L2, and these guys and L2 functions also give you distributions by taking the linear function you get by integrating against them. And then the Fourier transform takes this guy to this guy and preserves it. Same here, same here. But the problem, well, the problem is really that the inner product, no inner product on S prime of R, and it's maybe I think maybe that's the good way to say it. the problem is that when you take here, if you take the dual, you get the same space. Here you're taking the dual, you're getting something much bigger, and the things, things that are in here that are not in here are don't have a well-defined inner product. So so this is going to create a lot of raise trouble with your formulas. I mean, you're losing kind of the thing, which very often in the formulas, you want to kind of act as everything is going to behave the way it did in linear algebra, that all your operators are going to just behave nicely the way matrices behave. Well, you're going to really lose that because of this problem. So I think the thing to say about what I wanted to do with this is so as we go on, kind of, I think it's you have to realize that this is, if you really want to make sense of what I'm saying, of the statements that I'm making, and which are kind of often will be very standard statements from physics books, you really need to work in this context. And when you do this, the problem that you're going to always have is that you have to be very careful that you're right when you write things down, things that are in here but that are not in here. You have to be very careful about what it means if you start writing down the inner product. And so in the standard physics calculations, you often are going to need at various stages you're going to be taking inner products, and this is where you have to worry. So you have to be kind of careful. And I mean, I think one way of saying it is that if you're doing some calculation and everything makes sense everything makes sense if you stick to this, or even if you stay in, and if you stick to this, then you don't have to worry about distributions. But some calculations that you're going to do that like when you're going to start actually using these you're going to use the eigenfunctions at P, then you're going to be working in here, and then all of a sudden, the minute you start using one of those, you have a distribution, and you have to worry that this is now going to infect the rest of your calculations. So the rest of your calculations, once you've introduced something that really lives in here and not lives in here, is that the rest of your calculations are now no longer calculations in function spaces; they're calculations in a distribution space. And that you can work with a distribution space. You just have to be careful and not do. There's some things that you could do when you're in here, which you now can't do when you're in here. So you just have to be careful. So I think the general story about ways people deal with this is people mostly kind of ignore this problem and often work with these things as if they're functions and as if they have all the nice behavior. But then, when you hit a point where that causes trouble, then you start doing something to be a bit more careful and to treat them essentially as a distribution. Okay, maybe that's a good. So maybe it's a good idea to stop. So, are there any questions about this? This was kind of where I was hoping to get last time. Is this all making sense? No. Okay, so I think what I want, because then what I want to do, the other thing which I probably should have done last time is to say something about do a few quick standard examples that you should have seen, and then also say something about this Dirac notation. So let me first talk about Dirac notation. Okay, so as I said, the simplest aspect of Dirac's notation is that you take, if you've got psi is you just write down elements of the state space this way, the so-called Ket vector, and you've got anyway. So this psi is whatever you're putting here is just some kind of way of labeling what state you're talking about. But then you could have but then you define kind of things of this form. It's called psi. So these you can think of as being in the dual space, and then what you define then psi 1, psi 2 is the, if you like the pairing of this with this guy, but this the relationship between this and this is given by the inner product psi con. So this is just this integral. Okay. Okay, and so this is what this is true for psi element of L2. Okay. So this all makes kind of perfect sense for if I'm talking about states that are in L2. But what but now what the problem is that you really would like to what you really want to do is you would really like to extend this notation to this bigger space here and use it to write states in here, and then what you can do, then what you're hoping to do is then to think of okay, so the idea is but you extend to S prime of R. And so for instance, let's say what did I want to say? So for instance, P, we'll call P, if I write this P, that generally means the state e to the I P over H bar Q. And so this is an example of a non-normalizable state. It's an example it should be thought of as a distribution. This is not, you should think of this as something that you can integrate other functions against. And but then what you want to do is you want to okay. I'll work with this notation a little bit as we go through, but you want to use this. You want to use these to write formulas like in linear algebra. With P are basis vectors. I mean, the whole point of, one way to think about the whole point of these guys is that they really make very, very nice basis vectors for, they give you kind of a natural basis of the functions, which is distinguished by the vectors that behave as a one-dimensional representation under translations. So just as in Fourier analysis, as in Fourier series, these e to the I and theta give you a nice basis of functions on the circle. These guys give you a nice basis of functions on R, and they're distinguished by their behavior under translations. Okay. Okay, and then what we're going to do as we go on, we're going to see that you can then kind of write, you can then think of a lot of the formulas that we're going to write as formulas which are basically linear algebra formulas, but with these, writing out everything with respect to this basis. If you go back to that first option that I talked about kind of working with a kind of a fine dimensional Hilbert space and discretizing everything, then you can you'll get formulas that literally are the formulas from linear algebra. They really are exactly the computations of how to, of how to compute with operators with respect to basis and how to change bases. But here it's a little bit, it's tricky because you have, these are not dimensional spaces, but and their basis vectors are in this funny thing where you don't really have so your problem is going to be that inner products. Anyway, you're let me just say that your formulas are all about distributions. And you have to be careful what you're doing. Okay, so maybe let me just set some quick examples. I'm hoping most people have seen these examples, and if you haven't, they're pretty easy to test. So let me just kind of give you a write the basic examples down. So this is kind of just basic examples of Fourier analysis, and so examples of the Fourier transform. Okay. So one thing to do is imagine if you take f of q. If you take a Gaussian, then now if you take the Fourier transform of this, so f tilde. Okay, so this is going to be in my normalization. Whatever. E to infinity e to the minus I k q e to the minus alpha q squared. Okay, so I won't work through this calculation, but basically what you do is you shift by q goes to is it q plus ik over 2 alpha, and you shift this guy and complete the square, and then you use the fact that you can integrate this guy from minus infinity. There's a trick to integrate this guy from, then use integral minus infinity to infinity e to the minus alpha q squared. dq is square root of pi over alpha. And then there's a standard trick you should have seen when you can if you square this integral and rewrite it in polar coordinates, then you can actually do it, and you get this. And so you find and if you do this, you find that this guy is square root of 1 over, I hope I've got this right, 1 over 2 alpha e to the minus k squared over 4 alpha. Oh my God. And so the thing to notice here is that if you've got a Gaussian here with the alpha here it becomes an inverse. So if this thing is becoming more and more peaked, as say alpha is going to infinity, this guy is becoming less and less peaked. And so they had this kind of this inverse behavior in Fourier space and in Q space. And then you can also do the Fourier transform of a polynomial alpha q squared by taking derivatives alpha of this calculation. So if you take if you take the derivative of this guy, it pulls down a 2q alpha, and then when you take the Fourier transform, you can just use the way the Fourier transform behaves under derivatives, which is just the derivative of this becomes a multiplication by k. And anyway, if you take anyway, once you have this kind of formula, and you can actually you can get much more general things. You can integrate any polynomials times Gaussian this way. Anyway, I'm hoping people have seen this at some point. It's a calculation that occurs lots of places in math. Okay, and then the okay, so now for distributions, you have to be now all of a sudden you have to start being careful that what you really should do is you really should if you want to take the derivative of the distribution anyway we're going to, as much as possible, very often try to treat distributions as if they were functions, and we're going to follow what is typical in physics tests. And so you actually have to, if you get confused about what's going on, you have to justify this by going back and reinterpreting everything as a distribution, and using the fact that if you take the derivative of the distribution, you really want to take the distribution applied to minus the derivative of the function. You're going to use this adjointness relation, and there's a minus sign that in the standard definition of the derivative of the distribution, which gets put in order to, so that when you get the same formulas when you take derivatives of functions and of distributions. But let me just kind of go ahead and fairly naively kind of start kind of show the fairly naive calculations that you get into if you want to just kind of treat the kind of distributions you're going to be interested in as functions. So one thing that you want to do. So distribution. Well, let me start over here. So the main interesting. So there's two kinds of there's two main distributions that are going to appear that you're going to need to work with all the time, and one of them is kind of easy to think about because it's really just that e to the I k q gadget, and the point, and that it's very easy to think about that as a function because it is really just a function. It's just the fact that it really is only going to make sense if you if you integrate it against some kind of test function is some other piece of information. But if you're thinking about, if you're doing your calculations, the e to the I kq distribution is really not very problematic. But the most of the trickiness, then, if you haven't seen it before, comes from what's the Fourier. You also need the Fourier transform of that guy, which is which is the delta function distribution, and it's often it's not a function. But it's often called the delta function to make it look, because we're going to treat it like one. And then this is delta. So delta of q minus a. So it's a temper distribution. It's in this space, and it's so it's something that isn't actually a function, but you can, if you feed it a well-behaved function, you feed it a Schwartz function, you'll get a number, and the number you get is the thing that takes I want to say it f let's use psi of q. And so you feed this some nice test function, takes this to psi of a, just evaluation at a. Okay. So the thing about the delta function is from the so this operation is a linear function on test functions. It's just you feed it a test function, you get a number in a linear fashion, and I mean the definition is kind of trivial. You don't really need, none of the kind of tricky theory of distributions really applies here. It's just this guy. But then what you should do, the thing to do is you then, so treating this as a function, delta as a function, then what you want to do is you should think of it as a function that you can integrate against other functions. So this guy then becomes, you get e minus infinity delta of q minus a f of psi of q dq is equal to psi of a. So another way of kind of motivating these things and thinking about them is that these delta distributions are things that behave like functions, but you can't multiply them together and do a lot of the things you can do with functions. But you can integrate them against other things as long as the other things are well enough behaved. And the integration formula is just this. And then there's another philosophy for how to deal with these things is to treat them as limits of you can, for instance, take a certain limit of a Gaussian as you make the Gaussian narrower and narrower and go to 0 and treat them as limits of well-behaved functions, of limits of Gaussians. But yeah, and you may want to do that. But this is really all you need at this point. Okay, so in particular, but this implies that the integral from minus infinity to infinity of delta of q minus a. If I put, well, I mean, this doesn't quite imply because this is really only true on Schwartz functions. So now I'm going to enter a world of somewhat more mathematically dubious behavior, which is to try to extend this to something which isn't a Schwartz function. So if you put the function e to the, what was it, e to the minus I kq here, q, then that's right, q. Then what this says is that this should just be e to the minus I k a. But this is the formula that you expect. Well, these are now kind of somewhat dubious equalities, but this, so this is, if you look at this formula, this is the formula for the Fourier transform up to a up to a factor of 1 over square root of 2 pi. So this is okay. So 1 over square root of 2 pi. This is the Fourier transform of this. The square root of 2 pi times the Fourier transform of delta of q minus a. So if you believe that this nonsense, then what's true is that the Fourier transform of delta of q minus a is 1 over square root of 2 pi e to the minus I k a. Okay. So we expect, and it turns out that this actually, so this relation is based upon dubious manipulations because you're trying to do things with the Fourier transform that that don't make sense because these are test functions, not distributions. But this does make sense. So this is true. It's true as an equality of distributions. Okay. Anyway, so the physics texts are full of things like this, which are kind of derived as formulas for functions, but they really you can make legitimate sense of them if at each step of the calculations you say, okay, what's these are not really functions, but they're things that I know how to integrate against test function. Okay. Okay, maybe I should stop. So that's the end of the Fourier transforms. Now I think it's getting late, but I'm finally getting to the new stuff I wanted to talk about today. But this, which is the notion of the position operator. But this stuff is not so. But this, in some sense, is a very simple idea that once you have all this apparatus, you can then just quickly start talking about a different operator, which is basically the Fourier transform of the momentum operator, and which is the position operator. Okay, and then now just the quick things to say about this is the definition is going to be it's going to be an operator Q that if I apply it to some psi, which is some element of the state space, I get just the same function but multiplied by Q. Okay, and now, if you think about this guy, it's got similar problems to P. All of the analytic problems I was talking about, the problems with the P operator not being well defined and its eigenfunctions not being in L2, same story for this guy. So this guy, again, if you multiply an L2 function by Q, it may no longer be L2. And the eigenfunctions of Q are again, are not functions, but they're are distributions, and they're the delta of Q minus A. Let's say. Okay, and you can, if you play around with a legitimate definition of what this means as a distribution, you'll see that you get an equality of distributions, that Q operating on this guy gives you a delta of Q minus A. And then if you want, you can then think of writing psi of Q as the integral of minus infinity to infinity of delta of Q prime minus Q psi of Q prime dQ prime, as writing as expanding being in a basis. And we're going to think about, and these basis elements we're going to talk about are, again, you could write them this way. But again, they're going to be they're distributional gadgets. Okay. So this kind of is, anyway. So you can write down lots of stupid formulas like this, where you're really, but you can think of what you're doing as you're writing this guy as a sum of coefficients times basis vectors. But you've got it. There's a continuous basis, and so a sum becomes an integral. Anyway, there's a lot of ways you can play around with this and with the formalism. I don't want to say too much more about it, but let me tell you some interesting things about this operator. Actually, let me see. Is this is that all right? Is the blackboard readable? Because I'm starting to lose the light in here. Okay, so note, so Q P, and I think I'm running out of time, so I won't do this computation. But it's very easy. You've got two operators on functions of Q. one is multiplied by q, the other is differentiate with respect to q. Take the commutator, and you'll find that you don't get 0, you get minus I or IH bar, right? Yeah. IH bar times the identity operator. Okay. So one thing that so you can't simultaneously diagonalize Q and P. Okay. And you can think of what you've done is you can have two possible representation ways of writing H. One is psi of Q, functions of Q, and the other is through the Fourier Transform. Okay. And then these are related. So these are these are related by unitary. Let me just say this way. These are unitarily. Well, no, I better not say that. Better not say that yet. So, but anyway, there's a unitary transformation related by F, which is a unitary operator. So you should think of what's going on is that you've got a state space with some operators acting on it, like the P operators, and you can do and the P operators you can look at it either this way or this way, and here the Q operators are diagonal, here the P operators are diagonal, and you've got this Fourier transform is just a change of basis going from here to here, which is a unitary change of basis. And that's what's going on between a lot of the calculations in the subject, and you can write these things down. But now the other kind of important implications of this, besides the fact that it tells you that that you now know about two different ways of talking about H, and this is what physicists is often called a position representation, and this is the momentum representation. But I want to say, okay, but so one thing to note is that Q is that PH is equal to 0, but QH is not equal to 0. Okay, so the nice thing about the momentum representation, if you're dealing with a free particle, this is for a free particle. So for the momentum representation, you can simultaneously diagonalize the energy and P, and then so the way you move in time, the way Schrodinger's equation operates is very, very nice in the P basis. But it's not, and this just says that if you start out with a P eigenvector at a certain time, something has a momentum at a certain time, it's going to have the same momentum later. So momentum is going to be conserved. If you start out with a Q eigenvalue at a given time, which means you start out with a delta function at a given time, then you're not going to. It's not the fact that it doesn't commute with H means that it's going to immediately turn into something different, something very different. And I want to, if I'll get to the end, is to say what it is going to, what a Q eigenvalue is going to turn into. We'll see that in a minute. But Q and P look like everything is very, very symmetric until you remember that when you're talking about a free particle, this this is very, very different behavior. Okay, and then then just the last thing to say about it. Well, there's just a quick comment. I want to say more than this about this, but there's also Heisenberg Uncertainty, there's the argument. There's an argument in the book that says that if you've got if working with normalized eigenvalues, then you have that the expectation value of q squared times the expectation value of p squared is greater than or equal to a quarter. Anyway, so the argument for that's given. The argument for that just comes from knowing this, and it this basically this kind of characterizes kind of how, if you know, well, anyway, if you have some range of values for q in your state, if you've written it in some range, then the relationship between the range of values of q and the range of values of p, they're going to have some kind of inverse relation like this. And this is just the standard story. Everybody has heard that you can't. There's a specific limit on if you know what q is, how between what you know about q and what you know about p. And I won't. Let me leave it to a physics book to read a physics book for them to explain the physics of this better. Okay, so that's the main step. Then I just wanted to get to one last thing, which is kind of to answer. Maybe it's to answer this question of, we know what happens if you start out with a certain value of the momentum and evolve as a free particle. Your momentum just stays the same, but we don't. The question is, what happens if you start out as a delta function? If you start out at knowing exactly the position of a particle, what's it going to do at later times? Okay, and this is the problem of what's called the gadget, which tells you about this, is the so-called propagator. And one way of saying this is that we know that okay, so we know that the solution to Schrödinger's equation is going to be, anyway, I set h bar equal to 1, I have 0. I mean, so as an abstract fact, you know this. And that so now, if you're dealing with if you're in the momentum representation, so if your states are momentum eigenstate are given by this description in terms of k, then this guy is just going to be a multiplication operator. That the h is just diagonal in that representation, and you get that this is e to the minus. How did I want to do this? E to the minus I k squared over 2m. So e to the minus I has the value of e. So h is just k squared over 2m on these guys, psi tilde k 0. So if you want to solve a problem about how is a free particle moving, if you get it into this momentum space story, it's anyway. The story is very, very nice. It doesn't. I mean, all that happens is that it acquires this kind of anyway. It acquires this extra phase. But now, what about okay? So now, what about psi of q t in terms of Okay, so if we know the if we know the initial wave function, what's going to happen to this? So it's going to mean, in some sense, the answer is this, but this is now a differential. This is a second order differential operator, and you're trying to exponentiate a second order differential operator. You can't. Exponentiating a first order operator is just a translation, but a second order differential operator is doing something more subtle. And so what you want to do is you want to so you calculate by going to momentum space using this and then going back. So basically, you're going to do a Fourier transform of this guy, of the problem to momentum space, of this guy to momentum space. You're going to then evolve him this way, and then you're going to Fourier transform back. And that's what the propagator does. And I think, as I'm running out of time, let me just then. So this is kind of worked out in lots of detail in this section 12.5 about the propagator. But you end up with this you end up with this gadget. You end up with that psi of q t and q t is this is going to get confused. Okay, but so you're gonna so this is, yeah, you have to keep track of that. You got a psi of q0, but you just have to remember that this is the function at yeah, actually let me just write it this way. It's going to be 1/2 pi. The integral from minus infinity to infinity of this gadget, 1/2 pi times the integral from minus infinity to infinity of e to the I k q minus q0 e to the minus I k squared over 2m t. Then this is integrated with respect to k. Okay. And then you integrate this q0 with respect to dq0. Okay. Anyway, if you go through and do what I was saying in words here, you get this formula. Okay, and so the interesting gadget. So this is what's called the this gadget is this is the gadget which tells you it's the kernel that you use to integrate against this guy to get what you want, and he's what's called the propagator. And what I want to say about him, I know what I want to say about him. And in particular, maybe a good example is to say that okay, so this is u of t, and he only depends. So this is what I'll call u of t, and he only depends on the difference between q and q0, and u of t minus q0 is if you calculate him, he's the okay. So again, the problem with this guy, if you start thinking about how to calculate with him, what you quickly realize is that these are kind of really ill-defined. These are kind of, again, have this problem of being ill-defined integrals, but because they're really distributions. But if you go ahead and do this, So ut is what you get is that it's the square root of. But you know, this integral is really just a kind of Fourier transform of a Gaussian, but where the Gaussian has an imaginary coefficient. And so if you go ahead and use the same tricks for when you did for the Fourier transform of the Gaussian, you get something like this, m over I 2 pi t, and e to the minus m over 2 I 2 t q minus q0 squared. Okay, so you get a weird anyway. So I think one of your problems in the problem set is just to try to play with this guy and to start to try to understand him a bit better. And one thing that he's supposed to do, for instance, is that as t goes to 0, what he should do is, you know, at t goes to 0, he should just become a delta function. He should just become the thing which you feed this guy, you get back to the same thing. So he is going to be an interesting gadget that it's got that becomes a delta function as t goes to 0. But in general, the things to say, maybe just write this down. So note, watch out, is that this is a distribution. And so you have to kind of think of and one way of thinking what's happening with distribution is that you should actually think of him as a limit of some better behaved things that are actually legitimate functions. And I would say, and there's a bunch about this in the book, but the best way to think of him this is by take time goes to z is equal to t plus I epsilon. In other words, allow yourself to think about the complex time, and then here, if this is your time axis, then you've got a z plane, and what you can do, what you find if you put a non-zero epsilon in here, you find that on 1/2 plane, this is actually a really nice, well-behaved function. So it's going to be well-behaved on 1/2 plane. And then what you really want to do is you really want the limit as you really so this really should be the limit as epsilon goes to 0 in a positive direction of something in the z upper half plane, which is well behaved. Okay, and so this in some sense is a story where about a distribution which is kind of a boundary value of some nice holomorphic thing on the upper half plane, but it's kind of very, very badly behaved as if you try to think about this as a function. So anyway, that's just kind of a little, and this I think is kind of the beginnings of where you start to see that what you see later, what will come to some point later on, which appears later on, that if you really want to, it's actually a good idea in quantum mechanics often to kind of complex it, to think about, do what's called a Wick rotation and think about complex values of time, and then all of your, instead of distributions, all of a sudden your propagators become nice, well-behaved functions. So that's something I'll come to much later. But is there any, let me stop, I guess I better stop here for now. And are there any questions right now? Yeah. Okay. Anyway, I hope the hope I've skipped some of the details of some of the calculations, and they're done a bit in detail in the book. And I was trying to kind of give work out some examples of this Dirac notation of how you would do these calculations in this Dirac notation. And I don't think that was completely successful. I think I probably, looking back on it, it would probably, to the extent I was doing those, it would be a better idea to kind of, as I was working those out, kind of give the translation into the distribution language. I was becoming too much of a physicist in these and kind of just saying, there's some way to think of these as distributions. I'm not going to worry about it right now. It would have been a better idea. This would have been a very good place to worry about it. But anyway, it's that is what it is. Okay. Well, if you have any questions, yeah, could come back in a few minutes, and I'll be happy to talk to you about this or anything else. Okay.
Thank you.
Bye.
Thank you.
Bye.